Electric circuitry calculations. Here we don't involve Kirchhoff's law, but here we shall see some calculations that involve electric circuitry without involving Kirchhoff's laws. So first we shall see the meaning of drift velocity and calculations of drift velocity. We shall give a review of what we know about connecting in series, resistance, connecting batteries in series, etc, etc. Then we shall have a new thing, the potential divider and current divider. We shall review this. Again, we will have calculations involving temperature, coefficient of resistance, and we shall know what this is. Then we shall see electrical and heating and electrical power we shall see in circuits, and output and efficiency as far as electric circuits are concerned. So to start with drift velocity. Drift velocity, this is the average velocity with which electrons flow from negative terminal to the positive terminal when a uniform electric field is applied to the conductor. As I said, initially the electrons have random motion, so there is a need of a field to make them move in a uniform velocity. So on that state they start drifting towards the positive terminal due to that field set. So that's when we call that velocity drift velocity. Consider this circuit. Assume that we have a conductor. Assume that we have this segment of a conductor magnified so that is like a cylinder. So the drift velocity electrons are flowing towards the positive terminal there. Assume that this segment of a conductor is having length L and the cross-sectional area of this segment is A. Current flows in the opposite direction to the drift velocity, the flow of electrons. Current flows the reverse direction to the flow of electrons. That's why the drift comes here and the current goes the reverse way. So we know that current is the change, the charge passing over an area per unit time. So we have the charge passing per unit time. Let NV be number of charges per unit volume. Let NV be number of charges per unit volume. That means is number of electrons per unit volume. Where volume now we are defining this as a cylinder section of a conductor. So we have our volume as pi r squared L, where this pi r squared is the cross-sectional area A that we have said here. So remember, number of electrons per unit volume is number of electrons, Ne divided by volume. So to get our number of, because we are interested in the number of charges that pass in a unit time, so to get number of electrons, number of charges is equal to NV times volume. So you take this volume there, so we get our charges is equal to number of electrons per unit volume. So to get the number of charges, because this is the amount of charge, not the number, it's the amount of charge. So if NE is the number of charges, this is number of charges per unit volume, so number of electrons per unit volume. So number of electrons per unit volume, to get the total charge is equal to the number of electrons that are there times the charge of electron, which is E. So this in total brings the total number of charge that passes over this segment of a conductor. I repeat that current is equal to the charge over time, charge of this is the amount of charge, but let number of charges per unit volume in this circuit B is equal to number of electrons per unit volume, where volume is pi r squared L, where pi r squared is the cross-sectional area A that we assumed there. So number of electrons, to get the total number of the amount of charge, sasa to get the total amount of charge is equal to number of charges times the charge of electron. Because an electron as one has a certain charge E, but now we have total number of electrons on this conductor passing through this conductor as Ne. So to get the amount of charge in total is equal to the number of electrons times the charge E for one electron. So we get the total number, the total amount of charge that is passing over this length of a conductor. So from here we know that NE is equal to NV times the volume. So we have NV times the volume, which is AL. AL, remember, is the cross-sectional area here, AL. So you have NV times AL. When you take this volume there, NV times AL, we get this as the number of electrons times the charge E. Again, we know that time is equal to distance over velocity, and the velocity here we are saying is the drift velocity. That if this electron has to drift from this point to this point on the way as it goes to the positive terminal, then the distance that it covers, the length L, divide the drift velocity that we'll be using to travel from Y to X. That's what we call the time. So substituting in the formula here, that Q over T, we have our Q as N, number of electrons per unit volume, times AL times the charge E, divided by time, where time is given by L over Vd. So we can simplify further that if we cancel L and L, if L and L cancel, we remain with number of electrons per unit volume, NV, times area. Vd comes up. This is just mathematics. When you divide something down here, it goes up here. So number of electrons per unit volume times area is there, times the drift velocity times the number of the charge of electron. Then finally we can now find our drift velocity having an expression as I divided by N, you take N there, divide by A, you take A there, you take E there. So we have our drift velocity is equal to I divided by number of electrons per unit volume, divided by area, divided by the electronic charge E. However, sometimes you can manipulate further this equation, and we can find questions involving molar mass, involving densities, etc., etc. But if you remember from our knowledge of chemistry, number of particles, because the complication comes here because we have already involved number of particles, so we can manipulate it in terms of Avogadro's constant. We remember from our O-level knowledge that number of particles, according to Avogadro's formula, is equal to number of moles times the Avogadro's constant. Again, number of moles, is equal to mass over molar mass. So number of particles, which are the number of electrons per unit volume now, is equal to the number of particles divided by the volume. Number of particles divided by the volume. But number of particles we are given by mass over molar mass times Avogadro's number. As you can see, is N times La. N times La. So you put N, this is N times La. These are the number of particles. But this is number of particles per unit volume, so you divide by volume. I hope that is clear. The number of particles is equal to moles times La, where moles is equal to mass over molar mass. Now we have our moles here, we have our Avogadro's constant there. Now this is number of particles per unit volume, so we have to divide by the volume, where volume is given by pi r square L, where pi r square is the cross-sectional area AL. So we know that mass over volume, the things in yellow, mass over volume ni sawa na density. Tunaona hii hapa expression that mass over volume is sawa na density, so we can change this ikawa density. So we can have density times La divided by molar mass. Then finally we can substitute this here. Now instead of number of particles, we can put this here. So substituting this value, this part here, substitute Na with these values. Then finally our expression of drift velocity can be I times molar mass divided by density times Avogadro's constant times the area times electronic charge E. So our equation changes to be that way. We can solve some few examples here. That suppose we have a copper wire of a cross-sectional area x 4 millimeters squared, is 4 meters long, and carries a current of 10 ampere. The number density of free electrons is equal to 8 times 10 power 28 per meter cubic, number of electrons per unit volume. How much time is required by the electron to travel the length of the wire? As you can recall here, the drift velocity is equal to I over ni. I over ni, just remember drift velocity is equal to I over ni. So what they have written here, that drift velocity here, drift velocity is equal to I over number of electrons per unit volume times area cross section times the electronic charge E. So from here we have our drift velocity, but remember in our equation here there is no time. But can you recall where did we lose time? From here, you remember we started manipulating time from here. So we can see we have the distance L in the question. So we can use the formula to find the velocity, and we go back to find time. So you can solve for drift velocity I over NAE. So you are given the values, you put in the values there. Just remember, if you want the drift velocity to be in SI units, meters per second, you have to convert everything else in SI units. You have to convert this into SI units. That's why they have converted here into SI units here. Times 10 power negative 6 is to convert this into meters per meters squared. Again, we have electronic charge, and we have the density, it's in SI unit, there is no problem. And we have our length as 10, our current as 10 amperes. So it's put in the numbers, you get the answer is 1.95 times 10 power negative 4 meters per second. So the time taken by the electron is a length covered divided by the drift velocity. We know that the length of the current of the conductor is 4 meters long. Again, if we take length divided by the distance covered is equal to time. So we have the 4 meters long. If they are traversed, or electrons can travel 4 meters long, how much time can they use? They can use 5 hours. You can notice that drift velocities are usually very small. So just remember, when you are solving, most of the time drift velocities, the values are very small. If you get a very big value, for instance 10 power 5, you must know that something is wrong. That's a hint I'm giving you. Another question that you can solve here is that an aluminium wire of diameter 0.24 cm is connected in series to a copper wire of diameter 0.16 cm. So we're having an aluminium wire with diameter of 0.24. That is as if ameshatupa cross sectional area, because we know that diameter it relates to the area as pi d squared over 4, or we can change the diameter into radius and we have pi r squared. So first, find the current density in the aluminium wire. Find the drift velocity of electrons in the copper wire. Given that the number of electrons per cubic meter volume of copper is 8.4 times 10 power 28 per cubic meter. So we know from here we have aluminium wire, we have the diameter, so we can convert it to radius. We divide this by 2 and we get 0.12 centimeters. Converting it into meters times 10 power negative 2 meters. Again, we have cross-sectional area of the aluminium wire, because the question asks us in the aluminium wire. So we have the current density in aluminium wire. We have to find the current density in aluminium wire. So we know that current density is equal to current divided by cross-sectional area. I showed this earlier here. You remember current density here is equal to the current divided by the cross-sectional area. I said this. Therefore, from the question that we are given, current density is equal to current over area, but we can find the current by using our formula of, actually we are having current, we are given the current, the wires carry an electric current of 10 amperes. So we have our current and we have our cross-sectional area. From here we get our current density, simple as such. Again, in the second example, we are required to find the drift velocity of electrons in the copper wire. Given that the number of electrons per cubic meter volume of copper is 8.4 times 10 power 28. We know again from the copper wire that we are given has diameter of 0.16 centimeters. So we can divide by 2 to get our radius, 0.08 times 10 power negative 2 to convert it into meters. Again, the cross-sectional area x of copper wire is given by pi r squared, pi times the radius squared. You get our cross-sectional area there. And also we are given n as number of electrons per unit volume as 8.4 times 10 power 28 meters per cubic. And the electronic charge is there. We have our current because they are connected in series, so the current is just the same for each 10 amperes. So we have our drift velocity of electrons in copper wire is, according to our formula, the drift velocity is I over near. So we have current 10, electronic charge is there, number of electrons per unit volume is there, 8.4 times 10 power 28, and we have our cross-sectional area we have calculated here, there. So we get our velocity 3.7 times 10 power. As you can see, it's always small. Don't forget the units. So part 2, we are going to revise a little bit of what we know from what we have carried through since the first day we knew what is physics up to now. O level, we studied various connections of electrical components. We know the resistors when they connected in series, the resistors connected in parallel. We know cells are connected in parallel, cells are connected in series. So there are points to note. First, if we start with resistors, so we start with resistors. The first point to note is that assume that these are the resistors. They are connected in series in such a way. First point to note is that the total resistance RT is given by effective, the total effective. Now in the circuit, this is what the circuit will count, that we have a total resistance of R1 plus R2. That is what the circuit will count. That's the first point to note. The second point to note is that the current flowing through the resistors is the same. So current flowing through resistor 1 is equal to current flowing through the resistor 2 because they are connected in series. Another point to note is that provided that they have different resistance, they will have different potential differences across the resistors. So the voltage across them might vary depending if the resistance are the same or different. If the resistances are different, then the potential difference of voltage drop across the resistors will be different. For resistors in parallel, the first point to note is that total resistance is given by, when you are given resistors in parallel, the total resistance, this is how you go about it. It's just a revision, that you just write 1 over the total resistance is equal to 1. So you add them in forms of reciprocals. So it doesn't matter if they are 10, 16, 20, 100. Just write 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over R5, etc., plus until plus 1 over R nth resistor that will be there. So generally when you simplify to solve for R now, it's just mathematics. Now here I've used an example where I have simplest form where we have 2 resistors that is equal to the product of the 2 resistors divided by the summation of the 2 resistors. But the principle is there, that you add the reciprocals and finally you will evaluate the value of effective resistance. Another point to note is that these 2 resistors have the same potential difference, that voltage 1 across the resistor 1 is equal to the voltage across resistor 2 for whatever values of current that will be passing. Voltage across R1 is equal to the voltage across R2. Of course, the current that passes through R1, is not necessarily equal to the current that passes through R2, because when current comes here, it splits it there and another current goes there. So if these resistors have different values, then the current that passes there will be different, current passing here will be different. Though if the resistors have the same values, just like we did here to the voltages, here now to current, when the resistors have the same value, the current might be the same. But just remember that the voltage must be the same for parallel connections of resistors between R1 and R2. Coming to the cells, when the cells, these are passive components, so they have nothing special when they are reversed or when they are changed. Even if ukigeuza hii resistor huku pakawa huku, there is no change hapa. But for batteries it's important because positive and negative, these are like vectors, they mean a lot. When the batteries zikiwa reversed, they mean a lot in a circuit. But tukianza na cells in series, tukianza na cells in series hii hapa zinakuwa kama resistors in series, not in terms of resistance, no, but in terms of potential difference, that the effective voltage in this connection is equal to E1 plus E2. Now here, remember, if one of the batteries are reversed, then it should be assigned as a negative electromotive, because this is a force, so it can be positive or negative depending on the reverse direction or the forward direction. So if either one of these batteries is reversed, kwa mfano ukigeuza hii battery E2 ikageukia huku, then here patakuwa na minus. So the general formula is E1 E2. Just remember the directions of the cells matter a lot. We usually connect positive to negative, but if you reverse, not necessarily kwamba umeme hautakuwepo. Kama zinalingana zita cancel, as you can see here kwamba kutakuwa na minus. Kwa kama hizi battery zitakuwa zinalingana, then hapa umeme utakuwa hamna kitu, kwa sababu 1 minus 1 kwa mfano ni 0. So the direction matters a lot. Ndio maana kuna ukigeuza battery kwenye remote, kwa sababu zinakuwa zinalingana, remote unakuta ifanyi kazi kwa sababu ya kitu kama hiki. Umeona? But current that passes through the components is the same. Current that passes in E1 is equal to the current that passes in E2. Okay. Coming to the parallel connections of cells, note first that no matter how much you arrange, if there's any other battery here, no matter how much you arrange, this is just a wastage of energy, because eventually the effective voltage here is equal to just the voltage of one cell. Of course that is only true when the cells have the same value. Kama battery zote zinalingana, inakuwa ni upotevu wa rasilimali, kwa sababu connection ya namna hii ni battery moja tu hapa inatumika, ni unajidanganya hapo kote. Na inatokana na hii principle kwamba zikiwa connected hivi, potential difference inayopita hapo sasa potential difference inayopita hapo. Similarly kwa cells zote hizi lazima iwe kama ziko sawa, itakuwa ni sawa sawa tu na yule mmoja basi, kwa sababu itatumika tu ya mmoja. Pia hapa cha kuzingatia ni kwamba direction pia ina matter sana, lakini kuielezea ni somehow complex. Tutakuja kuona tukianza kusoma kwenye Kirchhoff's laws of electrical networks, lakini jua tu kwa sasa hivi kwamba unavyo connect batteries hivi huwa ni sawa sana na ya battery moja. So kama kuna battery yote ambayo ni ndogo kuliko wenzake, itakuwa haitumiki. Kwa mfano kama ukiconnect battery hii labda ni volti 10, hii ni volti 1, itatumika tu ile ya 10. Hii moja itakuwa haina kazi, itakuwa inapitisha tu umeme, lakini yenyewe kama yenyewe itakuwa haina mchango wote kwenye circuit. Similarly kama umegeuza battery, ni kwamba tu umeme labda hautapita, lakini battery itakuwa inatumika tu ni moja. So similarly kama hii hapa, huu sio kwamba utazifanya hivi, yenyewe tu ni kwamba total resistance itakuwa ni battery ya yule mkubwa ambaye yupo hapo. Kama zinalingana ni yule mmoja tu ambaye atakuwepo, any value of 1 ambayo itakuwepo. Kwa kama ni 10 zote zina volt ya 10, effective resistance effective potential difference hapa ni 10 tu. Kwa au kama ni 10 hizi nyingine zote ni ndogo, so itachukua ile the highest only ndio itakuwa effective resistance. Zikigeuzwa isamu complex, tutakuja kuona kwenye electrical laws za Kirchhoff's zile za electrical network.